Okay, so we're going to run through the physics of circular motion here. So let's start with the title. And you might wonder, why is it that circular motion gets its own kind of category in physics? And part of the reason is that circular motion is a very important part of the way that our universe works. Um, Objects orbiting other objects move in circular or very nearly circular paths, and it really helps to understand that motion and the motions in the universe by understanding a little bit about circular motion on Earth. So let's start with the concept of inertia and Newton's laws. So inertia, which in this case we're talking about essentially the mass of an object, right? And we know that the inertia of an object changes how easy it is to have that object's direction change, or to accelerate the object. Okay, so inertia is just the tendency to remain in motion or at rest. Okay, and we generally measure that in terms of mass, right? The heavier an object is, the harder it is to change its motion. Okay, so let's do a little thinking here. Well, let's talk about an object that's moving along. Okay, so here it is. It's a giant, heavy, spherical object, like a bowling ball, let's say. Okay, and that bowling ball is rolling along. Now let's imagine that we just leave the bowling ball alone completely. Well, Newton's first law of inertia just says that object will continue to go forever and ever and ever and never stop. Okay, but what if we want this object, instead of traveling at its constant velocity, okay, in a straight line, what if we want it to travel at its constant velocity in a circle? What are we going to have to do? If I want this bowling ball to move, instead, like say we're looking at this from above, we're looking down on it. Instead of just rolling straight, if I want it to follow a nice curved circular path, how is it that I can make that bowling ball do that? Spin it. Spin it. How do I get it to follow this? Oh yeah, don't worry. I know. Just gotta change the color here. Now let's say I want it to follow this path here. Okay, what am I gonna have to do? How can I make it do that? Gravity? Well, if we're looking down from above, this would represent, what's that? Ah, a magnet, maybe. A magnet might work. Like if I put a magnet in the middle and this were metal, it might suck towards the magnet. Sure. What else? Oh, right. Okay. So like if we say put a big funnel in the floor, it might follow the walls of the funnel. What if I just built like a circular wall here, right? And I just rolled it into the circular wall. Would it not start following the outline of the wall? What if I put a stake in the ground and I shot like an arrow into the ball with a rope on it? Then what is okay? What if I came up here and I just pushed the ball from the outside? Would that also work? Maybe like with a giant leaf blower or something. What if I just blew air on the ball? Could I then make it go in a circular pattern? Okay, what do all of these crazy methods have in common concerning the bowling ball? What do I have to apply to it? Ah, good. I got to put a force. And which way does that force have to point? Towards the center. So I need in some way, whether that is a tension of a rope, magnetic force, maybe even electromagnetic force, if I could do it, with like charged objects. Maybe I build a wall, so maybe then it's a normal force towards the middle. In some way, I need a force pointing, and the force always has to point towards the middle, right? Because I'm always constantly having to apply an outside force. If I stop applying the outside force, the ball just continues in whatever path it was going at the time, right? So let's say I do have this rope attached, right, and the ball's going around and around and around and around and around. And let's say when it's like right here, I cut the rope. What's going to happen to the path of the ball? Is it's going to use its inertia to just fling off over here, and this is a tangent to the circle. So Newton's laws help us understand a little bit about centripetal motion, okay? So we'll call this FC. All right, so we understand that it makes sense to us that in order to have something going in a circle, you have to constantly apply a force to the object that aims to the center, okay? So the force required for circular motion always aims to the center. Okay? And then what we would say is, we would say that the distance between the center and the circumference, as we would always call it, is the radius. So radius is important in this scenario. The radius is going to come into play. So let's think about this. We got this bowling ball ripping along, and we have a circle with some radius here, and therefore some circumference. What if I want the ball to travel on a tighter circumference but keep the same velocity? Do you think I'll need a higher or a lower force to make that happen? If I want to shrink this radius down to a much smaller one. Like, let's say a new radius is like this here. You think that that will require a lower force? Interesting. Let's say we want it to follow the green path. Okay, so if you want it to follow the green path, do you think you'll need more or less force than to follow the yellow path? More force. More force, right? I don't know if you can like intuitively understand why that is. We'll do it mathematically in a little bit, but intuitively, right? I think it's easy to say that if I have a larger radius, right, there's going to be less of an acceleration towards the center necessary. It's going to require less change overall in the direction. So let's maybe back it up a little bit. Let's say we have a circle that is of infinite radius. What does its circumference look like? Circle of infinite radius has what type of circumference? Would it not be a straight line? It's slightly philosophical, but it's going to help us understand this, right? So if I'm going in a straight, if I'm on a circle of infinite radius, I need essentially zero centripetal force to follow that radius, right? If I shrink that down to just a little bit less than infinity, right? This line will look almost straight, but not quite. So it should stand to reason that to follow a very slight curved line, I'm not going to have to deviate too much from my path, and therefore I'll have less force necessary, right? So continue that line of reasoning down to a very, very small radius. Well, that must require a very large force because you have to deviate off the straight path much larger. You're essentially fighting the ball's inertia. Does that compute intuitively? Maybe?
Swinging a ball.
Okay. Hopefully we didn't confuse you with this force thing because there's some confusion about velocity and time and period. There's questions about, well, what about when you're on the merry-go-round at the schoolyard? If you stand in the direct center, right, there's no force necessary to keep you going around. But if you go out to the outside, you can barely hang on, okay? The difference is you have zero velocity whatsoever if you're standing in the center. You have some velocity here, right? And you have some velocity here, but remember your period is the same, right? It takes the same amount of time to go this distance as it does here. So you're moving much faster over here. So it's not a direct, easy thing to wrap your mind around in terms of forces. Let's go to the math, and hopefully that can be some nice backup to help us sort of understand, you know, what the heck we're talking about here, okay? All right, so let's see here. So the first thing that we have to understand is, is that there's always an acceleration during circular motion. And let's figure out why that is. Okay, um, let's draw a circle again. Quite handy to be able to just like pull up a perfect circle whenever you need it. Although it's kind of a pain to change its color. Okay, there we go. Uh-huh. Uh-huh. Um, so let's say that an object has a constant velocity as it travels around this circle. Okay, so it's going around and around as a constant velocity. Velocity is a vector, right? And what does that mean? Well, that means that it has both a magnitude, right, and a direction. We do not have to change the magnitude of velocity to have an acceleration, right? If I look sometime later, right, so there's a delta t between these 2 points, so there's a change in time, there's a period of time between these 2 points, you'll notice that the velocity has changed, right? Not the magnitude, but the direction. So I'm changing the direction part of velocity, and that's where acceleration is coming from, right? And that should be easy to understand if you consider that the only force acting on here is towards the center. The force is always at a 90-degree angle to what the velocity is doing at a given time, right? So velocity is a tangent to the circle. Force is to the center. You would have a 90-degree angle in here, right? And so therefore, if the force is acting at 90 degrees to the magnitude of velocity, it can't be changing the magnitude of the velocity. There's no component of force in the direction of the magnitude of velocity. The actual value of it won't change. Just the direction. Okay? Hopefully that makes sense. Um, Now there's sort of a convoluted way of proving this. Let's see if we can do it. So let's say this is V2 and this is V1, and we want delta V. How do we find delta V, the change in velocity between these 2 points? How do we do that? Well, we'd have to do V2 minus V1. So if this is V2 and this is and this is V1. Oops, and this is and this is V1. Okay, so there they are, right? How do I subtract one from the other? Well, our way of doing that is to add the opposite vector, right? Do you remember that from before? If I'm asked to subtract one vector from another, the way to do that is to add the opposite vector. So this is the same as saying V2 plus negative V1, or V2 plus negative V1. So if I'm to do vector addition with this, it's going to come out looking something like this plus this, and here is our delta V. So I've just drawn on here, we might not have time to finish today, but we'll try. If we then look at this triangle that I've drawn here, so we've got R, so CA, and CB, and then we've got a chord between these two things. So what will happen is there's a time difference between A and B, right? It takes some time to go from A to B. Chord AB approaches arc AB on smaller and smaller time lengths. Do you agree with that? So if I make the time smaller and smaller, these get closer and closer together, right? And you can imagine, right? So we've got chord AB here, and there's clearly a difference in length between the arc and the chord. But as delta t, as the time shrinks towards 0, at time 0, the chord and the arc become the same, right? So what we're going to say here is we're going to say that this vector that we drew here can be likened to this vector here. Okay, so we'll put a little theta in here so we know what we're talking about. So if we draw it in this way here, so let's say we've got an R, and so that's that, so that would be like C to A, and then we've got like C to B we want, and then we've got our chord here, so this is our distance AB, Okay. And what we're going to find is, and sorry, this is V1, V2. We're going to find that these approximate each other. Or in other words, you get what we'll call similar triangles out of them. Okay. So give me 1 second. And oh yeah, and remember that this takes some amount of time, right, to happen. So time's important here. Okay, so all that being said, where do I want to go with this? Okay, so what we want to end up with, okay, is this concept. Okay, so here's my delta V, and here's V. So we could say, oh, that's the eraser. No, that's not what I want. So here's delta V and V. So delta V over V should be equal to chord AB, which I wrote as distance for some reason, but chord AB over R. Okay. So there we go with our similar triangle scenario. Now chord AB is actually a distance, isn't it? So it's actually a distance. So a way we can think about the distance is that on a small enough timeline, whatever the velocity is of the object going around the circle times the time should be equal to that chord, right? And that's over r. Okay. Now, um, now what we can do here is we can just do some rearranging. And give me a second. Sorry. Okay. I was thinking these were both r for a second, but I just wrote it poorly. That's actually velocity, and that's why I was confused there. Okay. So now we're gonna just rearrange quick, and we should get this. Delta V equals V squared T over R divided off T. We get delta V over T equals V squared over R. And what do we know that delta V is equal to? Delta V over T is equal to A. So centripetal acceleration is equal to V squared over R. Okay? And just because we're almost there, if I multiply both sides by m, I get m AC equals mv squared over r. Well, what's m times a the same as? Good. Centripetal force is therefore calculated as mv squared over r. Got it? All right, that's all we got for today. There's a centripetal acceleration and centripetal force.